Then, good morning everyone. I think that's everyone going to join us for now. As the slide may suggest, I'm Luke Williams. I'm here to give you the Natural Sciences Masterclass. But before we start, just like to say, Catherine's here today to help out with any translation, so if you'd like at the end to ask any questions in Welsh, she's very happy to help out with the translation there, because unfortunately I can't speak Welsh at all. I did my PhD at the University of Bath, just finished it there, and I did my undergraduate at the University College London. If you would like to speak to me about either of those universities, or about, say, studying in London, feel free to grab me. I'll be wandering around the exhibition at lunchtime, but I won't go into too much detail about those because I'll leave that to then. So, thermophilic chemurgy. Does that mean anything to anyone here? Excellent. So I put those two words together myself. Please go in. So, thermophilic chemurgy, I'll come on to the definition of what that is during the presentation. So, what am I going to talk about in more general detail? There we go. Start from the point of sustainable development. So, hopefully this is an area that you have looked at least in some detail somewhere across your curriculum. And in particular, we'll look at the energy sector as an example of that. Please? Yeah, fine. And the reason we look at energy sector is just to give you some sort of introduction to where I'm kind of thinking and to something that might be more approachable. Then I'll look at what a sustainable chemical industry looks like, because this is then going towards the kind of arguments that I'm looking for. And then finally, what is thermophilic chemurgy and how can it help sort of drive towards a sustainable chemical industry? So, sustainable development. Anyone here have their personal definition of sustainable development, or one they've heard that someone else believes? Anyone have any kind of definition of sustainable development that they would be brave enough to share? No? Oh, right. So, the most commonly held one is from Gro Brundtland, a former Norwegian Prime Minister who was asked by the United Nations to set up a panel investigating sustainable development back in 1987. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Now, it's quite clunky, but no one has yet come up with a better definition of sustainable development than that. The reason for that is it's a very complicated issue, and as we'll go through, it can be a lot more complicated than you might think from just first looking at it. It is really like a rabbit hole, and you can just get lost down there. So, is there any kind of other way of looking at it? And yes, there is. So, another way you could look at sustainable development is by looking at these three ideas. So, you have to have all three pillars of your argument together, otherwise whatever you're looking at is not likely to be sustainable. What you might have instead is one of these other secondary kind of ideas rather than fully sustainable. So to give you a couple of ideas about that, if we start from the social angle, people don't think that science really has any kind of social angle, but it does. You have to have the general acceptance of the public, otherwise your idea really isn't going to fly. So today, the good ideas for that would be things like fracking, genetically modified organisms. These are all kinds of things which are not yet fully accepted by the public. Now, you could argue that they should be, you could argue they shouldn't be, but this is the reason why there is a debate today. The environment seems the more obvious part of sustainable development. Mining, for example, where you dig up large tracts of land, contaminating things, chemical processes might use toxic materials. Fracking again comes up with this. You've got to be careful that you're not injecting things into the water supply. But more curious might be the economic side of things. This does not solely refer to commercial entities, businesses. It does also apply to things like charities and non-government organisations. They still have to keep going. They have to pay the people that work for them. So even in the most charitable of ideas, the most charitable of kind of products and things, there has to be some kind of financing. Now, this could be donations and things, but that's still not sustainable. You need to have something that continues over a longer period of time. Otherwise, you're going to have to keep looking for more money, for example, or rely solely upon the goodwill of people, and that can be a difficult thing to rely upon. So you need really all three ideas as part of whatever product or service you're looking for to remain sustainable. So, bit of a question for you: is renewable energy sustainable? So I've got the first example here: solar panels, solar power in general. Quick straw poll. Put your hand up if you think solar power, is sustainable. One, two, three, four. Come on, people, be more. Put your back into raising your arm. You know, if it's down here, I can't see it. You know. So about a third to half, maybe. So the rest of you think it's not sustainable. Is anyone willing to give an opinion as to why they think it is or is not sustainable?
I'll just let you know this session finishes at 12:05.
Thank you.
Thank you.
So no, Ilya?
Well, they're obviously going to break eventually, and they're not going to last forever.
Yep.
So someone's going to have to replace them in the future.
Yep, that's a good point.
If it's also occupying a large amount of land, you can look at it from the social side and have sort of the general public not approving it or find it sort of unbearable.
Yeah, some people don't like them. I don't mind them, but some people don't like them. Yeah.
I think to an extent they are sustainable, but if you think about it, the materials that they're made from might not necessarily be sustainable.
That's the point I'm looking for, the materials. So, yes, the land, yes, some people say they are or they're not, and also the important point is you can't always say something is yes or no. There's no kind of binary kind of something is or is not sustainable. You always have to look sort of graduations. There is a huge grey area. But yes, particularly right, the things that are made of. So in this case, the panels, you typically think of a solar panel made of silicon, kind of the stereotypical thing. That's actually not too bad because you can recycle about 90% of it, I think. You know, as things go, it's pretty good. And the last sort of 20, 25 years is kind of the benchmark these days. So the reason that we know they're recyclable is because the first kinds of solar panels are now being recycled because they now have come to the end of life. But the more important things is that people are looking for sort of more efficient solar panels. That leads them to materials like cadmium. Cadmium telluride, I believe, is the material used for some later generation stuff. Both of those elements are incredibly rare and quite difficult to obtain. So colleagues of mine have been looking at organic dyes as the kind of component that actually gets the electricity from solar energy. So those would be better. They'll be a lot easier to deal with. Potentially biodegradable, depends on exactly what they are. But the energy efficiency just isn't there yet. That's what they're trying to raise. And also there's also other layers in the solar panels which you'll also have to be a bit aware of as well. So we've got here wave energy. Straw poll again. Sustainable? Not sustainable? Any ideas? My biggest problem with wave is I've not actually seen any big scale stuff actually happen yet. Pilot scales, yes. No big actual generation of power. So they need to get on with that part. It may be there's some kind of big issue they haven't figured out yet. I don't quite know how they're going to get power. Is it going to be sort of tethered? I don't quite know that one. So they're going to have to think about that a little bit. Hydroelectric. Anyone got any ideas about that? Yep. They're thinking about putting one, trying to put one in the Seren. And they've been rebuffed simply because of the wildlife. But the amount of energy they're producing from that would be sufficient to power, I think, half the southwest and half of South Wales or something daft. There's a fairly large amount of energy you get to produce from one of the larger ones. But even more importantly than the wildlife, what's this made of? How much? Millions of tons of concrete. And concrete is one of the largest CO2 emitting substances that we produce. And then I've not actually known what they do at end of life of a dam, what the life of a dam is. The oldest one I know is the Hoover Dam, which I think is from the 40s or 50s or something, quite long ago. So that's still going, but these things are huge. Last one. Wind. Sorry?
Not sustainable, because the lifespan of wind turbines, although it's increasing, isn't particularly extended, and the materials that go into them, the social side of them, because they're made of steel and so on, that's from areas such as China, and finding in global areas, it's in part of the world. The environmental effects, their estimated lifespan is around 50 years, so you're equating multiple billion pounds worth of equipment in 50 years. And then there's the fact that they're not a consistent energy supply.
True, but you can, for example, in this country we've got, particularly Scotland, they're one of the best places in the world for wind turbines. But the materials, yes, again, the biggest case there is the turbine requires a magnet, and the magnet is usually made of neodymium. And to put it into perspective, if we wanted to replace every source of power we produce with wind turbines, we physically could not do it because we do not have enough neodymium available to do so. We would have to find an alternative source for our magnets. Big problem. There's also some interesting stuff I've seen about the effects that withdrawing power from wind, if you draw enough from it in a localized area, you can affect the weather patterns quite substantially, which is something to be aware of when they're placing large farms. People, for example, also come up with the idea that they kill birds, and that's a problem. They do kill birds, because they do kind of fly straight into them, because they're not always able to see the wind turbines very clearly. But coal actually kills more birds than wind. The extraction of coal, I believe, is. So you've got to kind of look through it. Yep, just to cover for that. So when you think about the materials something's made of, and the extraction of the kind of materials that you're making, the production process and things like that, you're actually going a bit further than just looking at the sustainability of something in operation. You actually look at the whole life cycle. So you start from literally extracting your metals, ores, or whatever they are. Processing and shipping is always going to be important. Packaging, there's been a huge movement recently on packaging in sort of supermarkets, but even packaging beyond that to suppliers can get a bit over the top. Shipping, you're flying stuff all around the world, which is quite common. Obviously usually now goes by ship, and larger ships and larger ships are being used. Some of the largest are truly horrendously large. They've actually had to sort of expand harbours and dig basically through to widen rivers and estuaries and things, so they can actually fit these ships through the canals as well. I think there was an expansion of the Panama Canal, I think it was, so they could allow even larger ships through. Again, you look at this kind of scale and you think this is just wrong, but it's actually a lot more efficient and a lot more sustainable to have the larger ships operate. Interesting, it's actually collapsed the shipping industry because of that, and I've clicked this again. So, shipping is obviously important. You see a product is the one that people look at. Okay, this thing is really just winding me up now. Yeah, so disposal is the key one as well. You've got to think about where you're going with it. Are you going to get rid of it? That kind of thing. So there's two ways you can look at it. Cradle to grave used to be a popular one, so starting to end. Then people thought, well, actually, you want to go a bit further than that, and so the new principle of cradle to cradle, i.e. the materials that you gain to start with, all the way through until your materials go into something else. And it gets a bit more complicated now, so you can go further and look at your, if you look at the kind of biological system, and so these brown arrows here are all the new ones. So the yellow is kind of the traditional route, you just produce something, distribute it, use it, and throw it away. What you can do is take the materials that you gain from throwing it away and recycle it. So this is like recycling boxes that you put out, kind of thing. Remanufacturing is when you take the materials, parts, and reconstruct a new object from them. And post-industrial recycling, so whenever you produce something, there's always going to be a waste of some kind. With a physical product, this can be easier to think of. People don't tend to think of it the same way as chemicals. When you produce a chemical, there are huge wastes, including solvents and some kind types of heat. So if you can use that in some other way, that's great. For example, a more emotional example might be the heat that they gained from, I think it was burning rubbish. They started with burning rubbish and then they moved on to the heat of crematoria and put that into heating a local leisure centre, which provoked a rather interesting media response, to say the least. So there are some very interesting ways of looking at this. Reuse as well, that's obviously popular. Covered all those four. So going further than that, you then have a concept called the circular economy, and I'll leave a short video to introduce that to you.
Living systems have been around for a few billion years, and will be around for many more. In the living world, there's no landfill. Instead, materials flow. One species' waste is another's food, energy is provided by the sun, things grow, then die, and nutrients return to the soil safely. And it works. Yet as humans, we've adopted a linear approach. We take, we make, and we dispose. A new phone comes out, so we ditch the old one. Our washing machine packs up, so we buy another. Each time we do this, we're eating into a finite supply of resources and often producing toxic waste. It simply can't work long term. So what can? If we accept that the living world's cyclical model works, can we change our way of thinking so that we too operate a circular economy? Let's start with the biological cycle. How can our waste build capital rather than reduce it? By rethinking and redesigning products and components, and the packaging they come in, we can create safe and compostable materials that help grow more stuff. As they say in the movies, no resources have been lost in the making of this material. So what about the washing machines, mobile phones, fridges? We know they don't biodegrade. Here, we're talking about another sort of rethink, a way to cycle valuable metals, polymers, and alloys so they maintain their quality and continue to be useful beyond the shelf life of individual products. What if the goods of today became the resources of tomorrow? It makes commercial sense. Instead of the throw away and replace culture we've become used to, we'd adopt a return and renew one, where products and components are designed to be disassembled and regenerated. One solution may be to rethink the way we view ownership. What if we never actually owned our technologies? We simply licensed them from the manufacturer.
I'm very happy with that. It must be this. Right, okay, so halfway through, what they're trying to get across is the concept where the economy, as I say, is redesigned to a more circular version. So they ended that part there on the idea of licensing technology, but you could go further than that and essentially send everything back to the manufacturer, have it restrip everything down for physical products anyway, and then what you do is separate the technological side of things, so your metals and that plastics and that kind of thing, from the more organic waste, separate those streams out, and then recycle both back in to be used elsewhere. And the important and key step from that is the fact that you need a lot of manufacturers to get on board. You can't just have one manufacturer with one product. You need to have the whole system working in concert, and that is starting to happen in many companies today. So the reason they were on about that is that losing resources. So when you say about resources, so surely we've got enough of most things, right? Well, not really. How many elements do you think we're likely to run out of in the next decade or two? Even 3 decades, sort of, in your lifetime, what we like to run off. Anyone have any ideas? helium. It's definitely one of them. We have an issue storing helium, and the US government has been selling it, so people have been buying it for things like balloons and things. Now, it's not quite as bad as people have predicted, because we are starting to find helium trapped in natural gas. There are a couple of, particularly a couple of natural gas deposits which have quite high concentration of helium in. So we're not going to run out, but we are going to need to start extracting higher and higher concentrations. So, you know, at some point we may run into issues. That's the issue we're looking at now. Each of those in red, 5 to 50 years of current extraction levels left. Now you might say, well, hafnium, when was the last time I used any hafnium? That'd be right. But then we've got things like silver, gold, platinum, so jewellery. And more importantly, what these things used for. Well, our society depends on these elements being around. I couldn't give this presentation, for example, because of the electronics used. So, to give you an idea, some of the uses, I could summarise that slide in 2 words as modern technology. So you've got, your alloys, so steel, basically variants of steel, but flat panel displays for indium. For me, more importantly, palladium, platinum, and the rare earths, because they're all catalysts for chemistry, without which we couldn't produce the variety of medicines and drugs that we need to survive. There are others there as well. But a lot of that is going to be modern technology. As I say, as a society, we've come to depend on these things existing, and if they didn't, we'd be in some sort of trouble, quite really. So this has led to the principles of green chemistry. So there are 12 of them, and what they were, because of the kind of growing ideas and understanding that this was happening, sort of in the 1990s kind of era, these kind of ideas were kind of formulated and put down to paper. So you can kind of sort of put these into categories. First one being safety, safer solvents. The obvious example here, things like benzene, which was used to be used as shaving foam basically. Benzene is highly carcinogenic, and we don't tend to use it in the lab anymore because it's too carcinogenic. But people were quite easily washing themselves with it only 100 or so years ago. Another similar example would be carbon tetrachloride, which is again carcinogenic and I believe has some other fairly nasty properties. So that's generally been replaced in the chemical industry with dichloromethane, so they just lopped a couple of the chlorines off. Still not particularly nice, but you do need chlorinated solvents in some cases. So they've basically made a small improvement there. And you might think, well, these are only small improvements. This is not good enough. But if you think about the scale of the chemical industry, a small improvement here and a small improvement there can add up quite rapidly when you're talking about thousands or millions of tons of product which are produced every year. So in this particular case, what I like to talk about, the time for degradation ties in very nicely with the circular economy. Catalysis is something we'll come on to now, and use of renewable resources, also very useful. Looking at biology as the answer. Looking at lignocellulosic material, which is plant material, is great. And so yes, catalytic reagents are very much preferred. To give you an example, I've done a bit of chemistry. I'm more of a biologist, but I'm not great at chemistry, so I was looking to do some oxidation, and so my colleagues recommended to me Des-Martin oxidation. That's quite literally the most simple form of chemistry. When anyone says chemistry, you think putting stuff in a pot, stirring it. That was pretty much the reaction. It took a couple of hours, it was great, it worked perfectly. The downside is the Des-Martin oxidant has a molecular weight in the region of 600, I think it's 681. I was using it for a pair of hydrogens, I then threw the rest out. So even I'm guilty of it. Something that's easy to do, something that's simple and quick and works is obviously going to be preferred if it's cheap enough, but the effects upon the environment are quite substantial. I've got absolutely no idea what's going on in this thing, apologies. Right, so chirality. So the principle of chirality, as like gain from that, if you have a molecule, in this case, has 4 different substituents on it, so 4 atoms or 4 groups, doesn't matter what it is. These 2 molecules here, although are identical in that regard, will have different chemical properties. And this is because they are what's called non-superimposable mirror images of each other, very much like your hands. And this is actually very important. The most famous example of this going wrong is the thalidomide issue back in the 1960s. Thalidomide was originally discovered to be good as a pain relief and for helping people sleep. It was then found to be good for treating morning sickness and therefore given to pregnant women to help treat their morning sickness. The problem is, one variant was great at treating morning sickness, the other one was incredibly good at harming unborn children. So therefore there were a lot of miscarriages and a lot of children born with things like missing limbs and that kind of thing. It was a horrendous tragedy, and this is why these days, if you wish to market a medicine, you must ensure that you are only producing one type of your material, or you have substantially proven that both types are non-harmful. What is more usually the case in a situation like this is you have one that's an active ingredient and the other one that just doesn't do anything. But in this case, you're still having to produce twice the amount of material for the same effect. What's even more concerning about the thalidomide case is that they were aware of this situation, and in that case actually what happened was the body is able to convert from one to the other, so it would not have mattered which one they provided to pregnant women, it would have both been just as harmful. So you've got to be careful with this kind of situation. Thalidomide is still being used around the world today as an effective medication. Currently more in developing countries. I believe it's currently being used in the treatment of leprosy. So it has gone around a fair bit. The reason I bring up chirality is because it's very difficult to get chiral products in chemistry. It's a lot easier for enzymes to do it than chemists. That's not to say that there are chiral products produced, it's just generally more difficult and expensive. So I'm going to look through one example, sitagliptin, which is a type 2 diabetes treatment. I'm not going to worry too much about the fine details of the chemistry, but I would like to point out some key points to you. So this is the first generation process developed to produce sitagliptin. And the things I'd like to point out about it are we have 1, 2, 3, 4, 5 steps. One at 83% yield, the next one at 81, and then from there it's 78. So if you multiply through the yields from start to finish, you're looking at about 51%. So almost 1 in 2 of mass molarity, however you wish to measure it, is being lost throughout the process. You're losing half your material, which is horrendous. On top of that, you've got, this is one of the catalysts that will help induce chirality because you go from there to there. Ruthenium, palladium, you've got hydrogen bromide, you've got triphenylphosphine, latter of which is used as a chemical warfare agent. So you've got to be careful with the kind of things that you use. Safety is obviously important, efficiency is also important, the overall sustainability of the process is quite important. So they moved to a second generation process, getting a Presidential Green Chemistry Award from the United States for their troubles. So what you can see here is you've got, they did things in one pot. They started from a different starting material and able to do it all in one pot. The advantage of this is you're always going to lose material when you transfer from one pot to another. It doesn't matter how careful you are, you'll always lose something. So it doesn't always matter how well your process is, you know, if it goes to 100% or not, you still might lose some of your material in purifying, which can build up. So that's great. They've also kind of reduced the number of harmful things they've got here. They've got a catalyst for a start, still got some rhenium, and then obviously some carbon. So there's carbon treatment for removing the rhenium. That's a problem. If you're working materials, you cannot provide metals for a medicine. So you have to go through some very, very stringent methods for getting rid of it, which obviously costs. It's annoying, but you have to do it because otherwise you'll poison your patients. Other important things here: higher yields. You've still got a couple of steps, but that's still going to be a lot better than the first one. And I'll also draw your attention to here at the end. So you've got 99.9% purity and 99.9% EE. EE stands for enantiomeric excess. Those two chiral molecules are called enantiomers. So all this means is you've got a very high quality product with a very high proportion of one of your enantiomers. Even at 99.9%, this is only considered good. It's not considered great. They want it as high as possible. So even after getting their award for this, they decided actually we'll do something and go a bit better. So these are the 2 hours that they're going for. So they first off went for this little improvement here. Still ruthenium, but it's slightly different. Very much higher EE, and that's a slight improvement. Great. They thought we'll do it even better, and we'll replace it with an enzyme. So here we're up to 99.95% EE. Again, it sounds like a very small improvement, but this small improvement is a huge benefit to the company. So they did that, and this is a transaminase. This is not a native enzyme. They looked at the native enzyme. I don't think the native enzyme could even do the reaction they wanted, but it could do a similar reaction. That enzyme, I believe, had 14 mutations in it. So why would you want to mutate your enzyme? Well, native enzymes are evolved to work in very specific conditions that are found in the cell. So very high protein content, typically very low concentrations of materials, because your body continuously, for example, your body or the bacteria will go continuously from one thing to the end of the pathway, so there's always a very low concentration of the intermediate steps. Obviously for industry, you want to shove as much material through as quickly as possible, so this is why native enzymes don't tend to be used for industrial reactions, because they're not always best suited for this. So where do I fit into this? Well, I work with this species called Geobacillus thermoglucosidaceus, rolls off the tongue, and I was looking at this particular reaction with an alkyl dehydrogenase. Now, again, it's also to do with the chirality, moving one to the other, and in this case it needed a second chemical to help it do its thing. But the important thing about this particular species is it's typically found in compost heaps. It grows at 60 degrees centigrade, and this is actually looked for thermophilic organisms, high growing organisms, are actually a large focus of interest at the moment, and the reason for this is because they have a lot of benefits. So the advantage of thermophiles: higher temperatures mean a higher rate of reaction, to start with. Now this is not always as beneficial as people first think. This is because enzymes that are native to thermophilic organism, i.e. they grow at higher temperatures, are optimized to work at, say, 60 degrees in the case of my stuff, and more normal organisms might be more optimized to, say, work at 37. Now the same enzyme in both organisms tend to have roughly the same rate of reaction at their optimal temperature. This means you won't necessarily gain as much from raising the temperature as you might think, which is a slight problem, but you do gain some other really good advantages, operating conditions. What I mean by this, things like viscosity. It means everything flows just a little bit better, and at larger scale that's quite important. Reactions that you can't do at room temperature might suddenly work because the thermodynamics changes. That's always useful. They found that chemical resistance So resistance to solvents, for example, uses the same mutations and same kind of changes to an enzyme as having resistance to high temperature. So this makes it really useful in industry when you might want to work in called biphasic, i.e. water and solvent, or even entirely in solvent. There are some enzymes that will work quite happily in the absence entirely of any water at all. Reduce contamination. Now, if you're running your bioreactor at sort of 37 degrees, E. coli, for example, other E. coli that isn't doing what you want, or yeast or anything, will go, oh, that's a great bioreactor you've got set there, I'll just move in, that'd be great, thanks. And you get a very nice contaminated run, which you might have to throw out the entire thing, particularly if you're using it to produce medicines. You're going to have to throw the whole thing away. Now, if you've got a bioreactor the size of this room, that could mean hundreds of thousands, maybe millions of pounds just thrown out. And also you've got to deal with a contaminated load of material, which you've got to get rid of somehow. That's not great. So if you're growing at 60 degrees, okay, my species would be very happy to live in that, but it has to get from wherever it is to that tank without dying. And trust me, if you look at Geobacillus wrong, it will die. It does not deal well with anything below 40 degrees. It will just instantly just go, just die. So it does protect you slightly from the issues that you might have from contamination. And the last, quite important in industry one, the kind of the business I was working with was producing ethanol. So Geobacillus is currently being used to make bioethanol from municipal waste, so kitchen waste, that kind of thing. So what they've got is like a Hoover kind of device that just sucks the air out from the top of the reactor. Because when you're running at 60 degrees, the ethanol will evaporate off, and you better just take that away. So I was going for the same kind of idea, working at 60 degrees, do the chemical reaction, and just suck off the product and use it. It's very, very nice, quick and easy way of looking at it. So, what kind of things was I looking at? These kind of things. So, for example, statins, antidepressants, perfumes, liquid crystals. Interesting case, liquid crystal displays. Excuse me. They weren't actually interested in which of the enantiomers. They just wanted one of them. Either one was great as long as it was pure. And this is a very, very nice example, raspberry ketone. Generally speaking, you want to go from the ketone, this bit, to the alcohol, because the alcohol is chiral, and typically alcohols are preferred by industries like the pharmaceutical industry because the alcohol is wanted, or the perfume because of the particular smell of a chiral thing. Best example of that is limonene. Limonene comes from citrus fruits, as the name might imply. One variant smells like lemons, the other smells like oranges. So if you're going for a particular fragrance, you're obviously going to want one over the other. Raspberry ketone, on the other hand, is, you may have heard of it, it's one of the latest diet fads. Take 2 pills of this, lose 63 stone in 10 minutes, or whatever they're claiming. Obviously it doesn't work, but that's not the point. The issue with this is people obviously like the word natural on the side of their packet. Natural, by European legislation, has to have no chemical processing steps involved. You're allowed to do biological, i.e. enzyme transformations, but you cannot do the equivalent chemically. So, although you can get raspberry ketone from raspberries, 3.7 milligrams per kilogram of raspberry, you'll be there for a while. The chemical process is very easy, cheap, quick, produces a load of raspberry ketone, but is not natural, so they can't use that process. So what they do is they extract the alcohol equivalent. It's called rhododendrol, so it obviously doesn't come from rhododendrons, but a larger quantity is found in the bark of the silver birch. So they strip the bark off, put it through a couple of enzyme steps, the last of which is an alcohol dehydrogenase to go from the alcohol to the ketone. And then you have your rather expensive raspberry ketone in pill form, ready to be sold to people who wish to have some sort of extreme diet. It's quite interesting, in my opinion. These are the kind of edge cases that you have to consider. So my research approach, I think I shall skip. So this was the result of my PhD. This is a SDS page gel, each one of these blobs here. some fainter than others, are one of my enzymes. STS page, if you haven't come across it, is where you put an electric charge through your proteins and they migrate down depending on the size of the molecule. These are just markers. So these markers are sized in what's called kilodaltons, which is the same as molecular weight for reference. So that's thousands molecular weight. As you'll see, they're mostly about that size. You'll get a little bit of variation, even if they are the same size. My personal favourites were 2 and 10, if you're interested. So, coming on to the concept of chemistry then. So what is chemistry? Right, these are black themselves. Right, so this was meant to be lignocellulose. So this is the source material, this kind of row. Lignocellulose versus oil. Chemistry itself is a branch of applied chemistry where you look at the production of chemicals from agricultural waste, usually. Agricultural materials. Lignocellulose is just generally all kind of plant material. So you could go from sort of your lignocellulose using traditional processing, existing chemical processing, to arrive at perhaps a new product. Or you might go from oil through using a new biological method of producing something to an old product that's already existing. You can mix and match these things. It was just a case of giving you a couple of examples. So you have lignocellulose or oil as your starting material, chemical or biological processing as your method of getting there, and you may have new or already existing products. It just depends on your aspect. There are people working on new ways of extracting useful starting materials from lignocellulose. There are also people looking at new enzyme pathways and new biological methods of production. You don't necessarily have to use both together, and I wouldn't advocate that you have to have a fully biological process to be sustainable. There are some very sustainable chemical processes out there already. Well, I don't know what's going on anymore. Right, so just to sort of get towards the end here, I presume you're more familiar with this kind of diagram. So the traditional way is distillation. You should look at the naphtha. So if you go a little bit further than that and look at the biological equivalent, we'll end up at the biorefinery concept, which is aiming to replicate the success that you get from extracting different parts of oil to extract different parts of biomass, lignocellulose, which is comprised of lignin, which is the big molecule which is very hard to break down, cellulose, and hemicellulose, and these come with different things. So cellulosic bioethanol is obviously a more commonly available one, but you can get loads and loads and loads of different molecules from it. So this is an example from the University of York, and the kinds of things that they've been looking at. So you've got your protein coming from it, you've got your lignin, which can be broken down into things like vanillin, vanillic acid, that kind of thing. Other things, using CO2 as an extraction method, you've got your waxes and things, you've got oils for biodiesel, you've got cellulose, break that down, form ethanol. Chitin or chitin, depending on your pronunciation, is the kind of hard stuff that crustaceans and crabs are made out of. You can crush that up and use it for a variety of purposes. It's currently being used as kind of like a bead-like material to put stuff on, which is quite fascinating. So, where I'd like to end is to just say that sustainability is a more complex issue than first imagined. It's often called a wicked problem, i.e. cannot be easily altered. Chemists are aware of the issue, and there is a move towards a sustainable chemical industry, and I feel that biology and biotechnology has a definite role to play in this, and I believe that the biorefinery is probably going to be the answer to the problems once we kind of figure out what we'd like to make biorefinery to be. Thank you very much. Any questions? Any questions? We've got a couple more minutes before the next session starts, and if you don't have any questions. Thank you all for coming.